All right, if everyone's back, we'll start back up. So this morning, first session, I talked mainly about what to do if you have a purely periodic calculation. In this block, I'll talk a bit about QMC for liquids and solids, and Carlo will pick up with another technique that you can use. So disordered systems, systems that you have to sample are more computationally challenging, right? I mean, you're competing with things like density functional theory, MD, and doing thousands of QMC calculations is daunting for most materials. So there's sort of three approaches that I think people typically take. One is to try to use a higher level method like quantum Monte Carlo to validate your choice of density functional that you're going to use as your workhorse. And possibly as an extension of that, you can say, okay, none of the functionals were great. I've got this tweak that I can make that brings them more in line with what the QMC is telling me. We can also look at doing thermodynamic integration. So this is start with some other method we think is close, touch it up with QMC. And then finally, what I put under directly calculate properties is what Carlo's going to talk about. For certain systems, particularly light elements, we can actually do the sampling directly in quantum Monte Carlo, and that's full CI QMC is the typical approach. So let's talk about the first of these. So we can use QMC to choose what functional we think will be best. So if people are familiar with DFT, you know that there's sort of a soup here. This is kind of a few representative ones, but there are literally probably at this point thousands of DFT functionals, at least hundreds, that you can choose. And there's no a priori way to choose which functional is going to be best. They're all kind of constructed in different ways. They all have different approximations. And if you haven't seen how they do on a particular system, you just don't know. And this includes sort of John Purdue has popularized this Jacob's ladder kind of idea. Okay, I'll start with local, then I'll add gradients or kinetic energy or full function or whatever. That means that the functional is more sophisticated. It doesn't necessarily guarantee that the results will be more accurate. So what do people in practice do? Well, often they'll say, okay, I've got this system that I'm looking at. I have some experiments in some range. Let's throw a soup of functionals at them and choose the one which reproduces the experiment best, right? So the problem with this, we may lose some predictive capability, right? Let's say there's a material that's new. I don't necessarily have any experimental data to look at. It's not always available or reliable. And also, it may be that what you have data on, your functional does great at, but the property you really want to calculate is subtly different. So this isn't a guarantee. Another option is to say, okay, I can't use my highly accurate method everywhere, but I'd like to choose the functional that best reproduces results from this more accurate method. So the advantage is you can hopefully always generate some data to compare to, and you can do it for exactly the thing that you care about. If this is bilayer binding, for instance, you can actually calculate a bilayer. So here's an example of this. This is from a paper that I'm a part of that was looking at the properties of Krypton under pressure. So Krypton's a bit of a pain for DFT MD, any density functional theory really, because the primary interaction, at least at the ambient, is mitigated by dispersion, right? So this is something that if I'm thinking about a semi-local functional that knows about the charge density right here, what's it going to know about the van der Waals coming from the charge density over there, right? Now that said, we want to do something, and there's been previous work, theoretical and experimental, that suggests, and I was caring about high pressure here, that at high pressure things sort of work out, that the van der Waals isn't nearly as important as the sort of exchange term that comes from pushing the cores together. So what we did is we looked at our cryogenic initial liquid, and we ran nice long MD trajectories with two functionals that we were thinking about using. In this case, AMO5, which is a GGA-like thing, and LDA, which hopefully everyone's familiar with. And the idea is to say, okay, if these things are sampling the appropriate Boltzmann distribution, right, they're getting the right partition function, they should be okay. So what I'm going to do is for every snapshot that I've pulled out, hopefully decorrelated snapshots, I'm going to calculate the energy with quantum Monte Carlo as well. And I'm going to see how the energy varies, right? So if you get something here where the energy is tracking pretty well, we'll say, okay, that seems to be sampling from the right Boltzmann distribution, it's getting the right thermodynamic quantities. Whereas for LDA, you can see that there's not really a lot of correlation between what the DFT, which are these red line connected points, and the QMC we're doing. So this was good evidence that we should use something more like AMO5 than something like LDA. Now this is pretty expensive to do these sort of calculations, so you'd like to develop some understanding rather than just say, okay, now I know what functional to go off and use. Now in this particular case, this was possible. Okay, so I calculated the energy versus volume with all of these guys. So basically take an FCC crystal, stretch it apart, squish it. And you can see here's the density of our initial configuration, right? So here's my LDA curve in red here. The derivative of this is going to give me the pressure. You can see this is in a negative pressure region. So what does the system want to do? It actually wants to clump things together to get sort of clumps of more ambient things. It can lower the energy that way. Whereas both the quantum Monte Carlo and the AMO5 are still in a positive pressure regime. So you get something that looks more like a homogeneous liquid. So this is, if you're doing a lot of quantum Monte Carlo calculations, you probably always want to have something more to grab out of them than just, okay, this one result. So this is an example of the sort of thing we try to do. Now this was all based on the total energy, right? I was looking at how the total energy from quantum Monte Carlo was comparing to the total energy of an approximate functional, right? So now you can actually benchmark properties beyond bulk thermodynamics. So for molecular systems, for instance, you could say, okay, how does the geometry compare? How does the bond length from quantum Monte Carlo compare to the bond length from whatever approximate methodology I want to use? It's a little more difficult in the solid phase, but you can do it. And here's an example of a paper looking at hydrogen, where they said, okay, in these different solid structures, if I compare the bond length from the quantum Monte Carlo in that solid to the bond length from these various density functionals, how well do I do? And you can see here that the air was, say, fairly consistent between the phases for this one property, and that one particular van der Waals density functional was doing best. Now, it's important to not just look at one thing in a lot of cases. So this paper also showed that the performance of the DFT functionals wasn't even. So for instance, energies were better with some functionals than pressures. So something to keep in mind. Now I mentioned that sometimes you can go beyond this, right? So we can say, I did this comparison, I benchmarked things, and the DFT still wasn't quite good enough. So an example of this is from this paper by Dario Alfe looking on small water clusters. So they did a lot of different snapshots with some DFT functional and then calculated with quantum Monte Carlo, have this large set of data points. And then they applied, in this case, basically a classical potential on top of the DFT calculations to try to bring things more in line. Okay? Now, this can certainly be done, and if what you really care about, let's say, is sampling this system, maybe it's a decent idea. However, you have a lot of worries about transferability when you do this. Okay, this worked for these small water cages, now I want to stick a sodium ion in. What do I do, right? So I'd be very careful. Also, to me personally, I worry about this sort of approach in that now we've added something empirical, let's just go to something like a classical potential that I can calculate very quickly. Why go to the DFT as well? But another option is that you can look in your DFT functional, for instance. So PBE sol was sort of based on the idea that the exchange term had some problems in it that you could fix up. If you have something physical like that in your exchange correlation functional, maybe using quantum Monte Carlo in this way makes some sense and will be transferable. So that's more along the lines of selecting what DFT or approximate method to use. Another approach that you can take is using diffusion Monte Carlo to calculate the thermodynamic properties more directly. So in this case, talk about thermodynamic integration. So the idea is that you can calculate the change in free energy from one ensemble, one interaction, let's say, to the next. Difficulty is that it can be expensive, and we'll talk about that. you need a large number of snapshots, and you hopefully want to have a method that is already doing pretty well. So here's an example coming from some of my work. We were looking at the melt line of xenon under pressure. So as you squeeze noble gas, it's going to solidify. As I bring the pressure back up, it should melt again. Sort of talked about Krypton. Noble gases can pose a problem for density functional theory from this van der Waals interaction. And there was some experimental motivation. In this case, the diamond Amble cell results here in blue had suggested that, okay, the melt line goes up in a Lindemann-like behavior, and then it flattens out. And that wasn't really well understood theoretically. Most people that had looked at this had sort of found, okay, things should just keep on going up. Now, is this because they had used DFT that had some deficiency in it, or is maybe something going on in the experiment that's not understood? So this is going to involve a lot of computation. You want to be able to answer some of these questions, like I said. Is your quantum Monte Carlo really doing quite well? Are my pseudopotentials good enough? Are my nodal surfaces good enough? That sort of thing. So I spent a lot of time looking at the xenon pseudopotential in this case, and found that we really needed to include, say, the D projector in the pseudopotential, even though the valence electrons I cared about were only S and P. So something to always have in the back of your mind. In this case, this is before I had done a lot of this benchmarking on dimers. I actually benchmarked by looking at the energy versus volume curve of FCC xenon. So here I've plotted in blue that you probably can't see, results from one density functional that I was going to use as a trial wave function, and from another density functional. Now, the thing that gave me a fair amount of confidence that the nodal error was going to be small is that starting from both places and doing the quantum Monte Carlo calculations, I found a result that fell right on top of one another. So within this sort of limited choice, I found that the nodal surface in quantum Monte Carlo wasn't very sensitive on the DFT that I used. So okay, I'm pretty confident that I can do calculations on bulk xenon. How am I going to use this to look at the melt line? So you can do thermodynamic integration, or you can just do a one-shot thing. So the way this works, I want to calculate the change in Helmholtz free energy from one ensemble, which is my DFT ensemble, to my quantum Monte Carlo ensemble. That's going to be harder for me to sample, right? So I can just write out the partition function there, and you can come up with some expression, for instance, that says if you sample in your first ensemble, your DFT, and you calculate the change in energy as you go to the quantum Monte Carlo, which we think will be more accurate, this is going to be the change in the Helmholtz free energy. Now, it can be a little bit dangerous in that we really need to sample everywhere, and there could be places, for instance, where the configurations are very unlikely, let's say in your DFT. And just doing, say, this sort of change in free energy between snapshots could lead you down the wrong path. There are also sort of more perturbative expansions. You can write this down in terms of cumulants. And hopefully, we do these two things, we'll get a pretty similar approach, and that gives you maybe a rough idea of the convergence. Now, that doesn't necessarily solve the problem of what is the initial free energy of, say, the liquid or the solid at a given density and temperature. So I didn't actually calculate those free energies directly. What I did is I wanted to say, where are they equal? And the way I did that is within density functional theory, I used coexistence simulations. So basically put the solid on one side of your box, put the liquid on the other, run a long time at a given temperature, see if the whole thing melts or the whole thing freezes. So now we know that the free energies of the two things are matched within a fairly narrow window here. Now what we're going to be doing is have, MD calculations that are going to sample our Boltzmann distribution, and then we're going to do quantum Monte Carlo calculations on those snapshots. Now I mentioned that we're going to use a spline representation. In this case, that resulted in way too much data to store on the nodes I had available at the time. So I was getting a 96 gigabyte wave function. So this is one of the examples where we were using this hybrid representation where near the cores of the atoms sort of represent things on a radial spline, and then in the interstitials used the coarser mesh. And this brought the size of the wave functions down to something I could handle. My nodes at the time had 32 gigs. Great. It was kind of expensive, but this can be very well parallelized. Now in practice, how did this look? Okay, so I had a bunch of different snapshots, decorrelated snapshots at a given density and temperature from my DFT calculations, energy sort of given the red curves. Then I did calculations with the quantum Monte Carlo. And you can see sort of by eye here that it looks like the shift is pretty much rigid between them. So we did this in the solid and the liquid, and here's what happens if you sort of subtract out this rigid shift. So that gave me some idea that the ensembles, the relative sampling of the configurations was pretty good. There just happened to be an error, let's say, in the liquid energetics or in the solid energetics. Compared the free energy shift from that exponential form, that one shot, to the perturbation series, and you can see this converge very quickly. So I thought, okay, I've got some pretty good method of calculating the change in the Helmholtz free energy. What I really wanted to know is change in the Gibbs free energy, or the change in the melt line, right? So there are two ways to do this. There's a paper that uses this technique, although thermodynamic integration has been around for a very long time. But Sola and Alfei use this to calculate the melt curve of iron under pressure, where they basically said, okay, the change in the Gibbs free energy is related to the change in the Helmholtz that we've calculated with our thermodynamic integration, with some corrections due to the isothermal compressibility and the change in pressure going from DFT to quantum Monte Carlo, and the change in entropy in going from the liquid to the solid phase. So you can make reasonable approximations to these things, but there's sort of parameters that you may not know as well. An alternative approach that we also did is, let's work directly within the Helmholtz free energy. So at the same temperature, let's say along an isotherm, how the Helmholtz free energy is going to change, and then you can basically just calculate the change in pressure from the Gibbs construction. This requires you to do calculations at different densities, but okay, it can be done. And if we do this is sort of an example of, okay, here were the red and blue lines from the DFT calculations at different volumes. Here are my corrected values of the Helmholtz free energy from quantum Monte Carlo. That allowed me to calculate the change in the pressure, let's say, from going from one ensemble to the next, compared to the Alfei method. So everything works well, and you find that the sort of Lindemann-like behavior held. So in this case, and this is always dangerous, you should always be very cautious when doing this, but we suggested that perhaps what the experimentalists were seeing was not actually the melt, that it was really a solid-solid phase transition that looked funny in their particular experimental setup. So I don't know if anyone has any questions on these sort of cheaper methods. If not, I think Carlo Pierleoni is going to talk about actually directly sampling the distribution using quantum Monte Carlo.